Hi, welcome to this lecture. Today I'll be talking about some basic statistics. For many of you, this will be a refresher, and it will be covering information that you've likely taken in any social science undergraduate statistics course or some types of tests and measurement course. So let's start with measurement. So how we may measure variables, I'll go into different types of variables, but measurement is the central issue in the science of psychology. It's the act of assigning numbers to characteristics of objects according to certain rules. So these include things like attitudes, personality characteristics, performance, like job performance or extra role performance, or cognitive capabilities in general. We often use the term constructs to describe these types of concepts that we're measuring, psychological constructs. In the 1940s, measurement became a much more central issue, especially in IO psychology. Stevens covers this in his writing on the theory of scales of measurement, where really defined the scales and described when the best time is to use each type of scale measurement. One thing to keep in mind is that there's different levels of measurement. So for this, what I mean is that numbers at different levels in terms of what a concept means really can convey different types of information. So some examples here to help illustrate what levels could be. A level could be data that is describing a within person characteristic, something that's happening within one person over time. So this is often going to be measured through things like a diary study where somebody's putting in multiple entries. Also, it could be between people at the individual level. So this is most commonly seen in things like a survey, an engagement survey in the workplace, where you're comparing 500 different workers on something like a characteristic of engagement or job satisfaction. Or it could be measured at a team level, at a group level. This is most commonly measured by taking individual assessments at the between person level and aggregating it to a team. So the average of the 10 employees could represent a group phenomenon. Or there is a way that we could look at cross level types of analyses. And so for this, it's taking two of the different types of levels that I've described and looking at relationships between them. And this can get a little bit confusing, but the general idea is that uh, a variable that you measure at one level could affect another type of concept. So, job satisfaction of an individual worker might affect the overall team's performance. So, a really unhappy worker might poison the entire group's performance. There's special analyses to test out these types of relationships. They would be called cross-level interactions and cross-level analyses. That will be beyond the scope of this course, but I want you to know that there are different levels of assessment, and you really should take caution when you're trying to generalize the findings at one level to another level. There are different types of measurement and measurement variables. First one I'll talk about are nominal. So this is often the kind of the simplest one in terms of how to measure. It's going to be the categories or the classifications that you put people into. These are all objects must be placed into mutually exclusive and exhaustive categories, things like a major of college students. So all students will be put into different groups. The way that you report a nominal variable is through a count or sometimes a proportion or a percentage. So there are 60% males in a sample versus 40% who identified as female. Because we're looking at categories, we do not have a normal distribution of responses. People are going to be placed into different categories, and that's what is meant by non-parametric. So when you do not have a normal distribution, you have to use certain types of tests to see if there's significant differences between groups. we'll talk a little bit more about a normal distribution in the first couple lectures of this course. But I want you to know that when you're looking at categories, you have to really use a different type of analysis than what you would use for other type of scales. The next up is an ordinal type of measurement. And so this is a type of classification, but it's also a rank ordering. And we see this very much in almost all types of measurement. It could be most of our psychological measures. We see it very much in grades of courses. So A is better than B, which is better than C, which is better than D. You also will see it in how we will measure attitudes. So often people respond to a question about job satisfaction or engagement on a Likert style of scale. And that will be strongly disagree to strongly agree. As a result, their response is into different categories of agreement, which we rank order. Interesting part about ordinal, there's no real absolute 0 point. And the really important thing is that we don't have a lot of information about the differences between the scale points. So no information about the magnitude of the differences between these categories. Is strongly agree very much different from neutral compared to strongly disagree? We have no real evidence that the distance between our points on an ordinal scale really have equal distances. And so that's one point to keep in mind when you're dealing with ordinal. We assume that the difference between a 4 and a 5 on a 1 to 7 scale is the same as a 3 to a 2. But again, that is an assumption that we're making. Next up is interval. So these have all the properties of the nominal and ordinal scales, but there's equal intervals between the numbers. So I was just going into how the intervals may not be equal in ordinal scales. Interval, that's a key factor, a key feature of it. A great example of this is temperature. So the difference between 99 degrees and 98 degrees is the same as 55 degrees and 54 degrees. We can also have a ratio type of measurement, and all of the properties of the other, except there is a true point of 0. So height, you can't go negative in height. Each of these have different operations that we can attach to. I think it's good to keep in mind what those would be. Obviously, if you're dealing with categories, such as nominal, all you can really do is say if the groups are equal or not equal. The way that we would evaluate that is through a non-parametric statistic. So that means statistics that deal with non-normal curves. And it's primarily categorical is a simple way to describe it. And then you can see here the different logical and arithmetic operations. It's good to remind yourself of what can go into those. So do the different types of measurement affect our statistics and the analyses we run? Well, it depends. There's been debate over the years that some scales might have a different type of effect on our findings. Ultimately, when it comes down to it, is the effects that it might have in how we measure something might be rather small. The more impactful thing is how the scores are distributed and what the shape of that distribution is. And I'll go into what distributions can look like later in this lecture. So it may not matter as much about how you're measuring it as long as you're getting a good distribution and variability in your response options. So sampling in terms of studies, we're going to be talking about population versus sample. You're likely familiar with this, but the population is everybody that you would be considered to include in a sample. So this is the collection of people, things, events, or scores that have some common characteristic. This could be represented by everybody within an organization. That is your population. You're not interested in studying anybody outside your organization. And so when you do perhaps a survey within an organization, that could most likely be a sample if you're only collecting a subgroup of that organization. So any subgroup of that larger group is considered a sample. And then we make statistical inferences about the population using these samples. So we're not able to describe the entire population, but we are making inferences. It's important to recognize that this is inferential statistics. We're using a small portion of data to try to describe a larger group that we do not have information on. So sampling is often going to be done through random sampling or probability sampling. So the odds of selection are known and calculable in probability sampling. A good example of this is jury duty. If I know that I have a 1 in 200 chance of being selected, so the odds are set, they're very clear. In order for me to do this, where I have clear odds for everybody to be participating in my sample, I really need to know what the exact size of the population is. That way I can assign everybody a certain type of odd and probability. Every member must have a specific probability of selection, and its random, unbiased selection is used. There's different types of probability sampling that I want to give a little bit of information on, but it's important to know that there's different approaches that you can take depending upon how much access you have to your population. So first off, simple random sampling. You can just randomly sample everybody within your organization or of your population and see what happens. Or you can do a more systematic approach. This is sampling with an interval. And so an example here where you're using an interval to do your random sampling is every fourth employee in the organization is going to get sent the email to do your survey. So it's an interval there of 1 out of 4. The stratified random sampling is that you're separating the population into subgroups and then randomly sampling from each of those subgroups separately. So randomly sampling within females, and then again doing a random sample within males. This way it will lead to equal proportion of both genders in your sample, but you were able to still use random approaches within each subgroup. The next up is proportionate stratified random sampling. Simply here is you're ensuring that a proportion of people in your subgroup match the overall population. So your subgroup, if you're working in a female-dominated organization, your sample will have more females in it, but you were still able to randomly sample within both of those subgroups. Cluster sampling is the last one there listed. This is when the population is going to be divided into clusters, usually by quote-unquote natural factors. So things like where a person lives is a common one in social science. So if you've lived in a certain area of blocks or a zip code, you're going to then be random sampled in that cluster. I think a good one that happens in IO psychology is often random sampling within a branch or a division of an organization. There is sampling bias that I want you to be aware of. A common one that we see, especially for graduate students and in university settings, is sampling only those who are easy to contact. So we see this for master's thesis. We see this in the concept of exit polling. Oftentimes you'll see it in organizations where people might do a sample of only those who they know, or they can easily call up on the phone or send an email to that they think will respond. This is a bias because you're only getting a certain type of person to respond to your inquiry. Last one there is sampling only those who invite themselves. This is common in internet polls or online types of surveys where people are self-selecting into it. But in another form of sampling bias might be looking at an organizational program, and you're only able to sample people who self-selected into the program. And so if you're trying to evaluate a fitness program or a wellness program, you really do have a sample bias. It's probably going to be the people who are most in need of the services or who already have a natural tendency to be active or healthy or engage in a type of program like that already. So sampling bias isn't just in surveys, it's often shown up in program evaluation as well. Great example of this is the landline only polling 2010 research study. 25% of households are cell phone only, whereas 29% of US adults 25 to 29 only have a cell phone. And what happens is if a cell phone only is used in this type of research, your sample is going to be more likely to be young, less affluent, unmarried, and liberal. And so doing a certain type of approach to collecting your data is very much increases your chances of having a bias play out and altering your results. We saw this as a great example in the 2016 presidential election. What was predicted was far from what actually happened. The early polling before the election very much showed Hillary Clinton taking over Donald Trump in terms of the popular vote. But however, the popular vote, although still in favor of Clinton at the election result, was much smaller than any poll was actually reporting prior to the election. So again, sampling bias very much played a role in that. We can see that in two of the polls here. The 538 prediction was wrong about 5 states. Really, why might have that been? There was a sampling bias related to non-college educated voters. This all relates to non-probability sampling. And so we talked about doing a random sample, but non-probability sampling is when members of the population do not have an equal probability of selection. So it's non-random. Perfect examples of these are convenience sampling. So the researcher collects sample from those they have easy access to. Also quota sampling, so ensuring that the sample has the same demographic proportion as the population. So again, it's not random there. You may have reasons to get that quota, and it's worth jeopardizing the randomness of your sample. A common approach also is snowball effect, snowball sampling, where you're trying to collect data. So you maybe share a survey link on LinkedIn and then ask everybody that you know to fill it out and then share it to all of their friends and colleagues. This is a common approach in theses. You will also see it sometimes in organizations where you'll share a survey or an opportunity for research with one of the people in the organization and ask them to share it and spread it. And so you'll often use a lot of strategies to collect data because in organizations, it's less likely you're trying to do a random sample. You're trying to get really a entire population to maybe do your survey or get data on your entire organization. So you're going to use a variety of these methods. It's just being aware of the approach that you're taking and that really what it is that's going on in terms of your data collection. So does this really matter? Well, it's debated. And so especially in applied psychology, you have to just weigh the scenario and weigh your options, evaluate what your options could be, because oftentimes you're trying to get as much data as possible. If you're doing research, though, that could be a big problem because collecting data on college sophomores and juniors may not be representative of the population that you're really interested in. So it very much could be a problem if you're doing more of a research focused job. But the people who say it's not too big of a deal, it's because really if you don't have a random sample or you've used quota sampling or you've done snowball effect or convenience sampling, it may actually be due to the fact of increasing your external validity. You're trying to put in an effort to get a hard to obtain sample, something that you can't study in a laboratory setting. So anytime you're in an organization, it's not something that you have a lot of control over. It's a real world setting, and as a result, it probably outweighs to collect the data in the organization than doing something in a laboratory setting or a college student or maybe on the internet with a sample that you're paying for. So it's very much a debated topic. Let's move on to distributions. This is how your data is variable and what it looks like. So here's just a distribution. You'll see that we have an N of 40, a large number of responses over here on the right hand side, and then skews towards the left with very few responses. This is actually to represent the Milgram experiment, so you're probably familiar with that, where a large number of people responded with the XXX shot. So this would not be a normal distribution. This would be describing really where the responses were coming from in terms of were they in the middle of an average score, all centered around the mean, or were they widely variable across all the answer options? In this case, they clustered towards the high end of the scale. In order to understand a distribution, we have several descriptive statistics. First off is the mode. This is the most frequently occurring score in your data. So it's a simple count of the variable in terms of how many responses were provided for each scoring option. It can be useful, especially if your data is skewed or if your data has restricted range. So in the prior example, we could see that in Milgram's distribution, the mean might not be a good description here. However, we could describe that the most frequent response was XXXX. You'll most commonly see the mode be reported in organizational settings when it comes down to program participation. Who was the most likely to participate, for example? What category of person was most likely to participate? Next up, we have the median. This is the middle score in the distribution. The way you calculate it is arrange all the scores from highest to lowest or lowest to highest, so put them in numerical order, and you find the middle score. If there are more than one middle score, you average those two middle scores. This is also very helpful with skewed data. So it really gives you an idea of the middle point when you have that. We're going to talk a lot about the mean and the average score. That's going to be very much a central piece of regression analysis and correlation analysis. The equation of regression analysis is heavily dependent upon the mean. And so it's really important to understand what a mean is and how it might be affected by your data. So the mean is the most commonly used measure of central tendency. It describes the middle point. It is the average of all the scores. So we have the equation there where you're going to add up all of the variable scores and divide it by the number of scores that there are. So we can see an example here. If you add up 57, 69, 72, 81, 86, and then divide that by 5, the mean for this set of scores would be 73. That gives us an idea of what the middle point would be. So it is very much an indicator of central tendency. It is what we often call a true center. But the mean is very flawed. It very much can be influenced by outliers. An interesting point about the mean is that if you look at how much each score differs from the mean and then add them all up, it's going to equal 0. So the sum of how much each score differs from the mean is 0. So that's why we often refer to it as the true center. Next up is deviation. And this is another word for variability. And so when I mentioned how the mean is a key statistic in regression and statistic analysis, so is deviation or variability. So why do we care? Because there actually is variability in real life phenomenon. So in terms of individual differences, in every variable, people differ. No human being tends to be exactly alike, and so there is variability naturally occurring in the real world, and so we try to capture that variability with our statistics. There's also variability in our measurement, and so any factor entering into the measurement process that is different from the actual construct that we're intending to measure, that would be called error. And so there's variability in terms of just how we try to measure something because of this error. It can be due to random fluctuation. It can be due to environmental factors, something we didn't account for, or when we collect data in one setting, it's different from another setting. Or the device that we're using to measure something may be unreliable. It's not a good tool that we're using. So there could be variability in terms of error, something that we're not intending to capture. So indices of variability give us an indication of the shape of the distribution. So how the scores are different from the mean is going to be captured by variability statistics. And so the shape of this distribution of how the scores differ is very important for us to understand, is very important for us in understanding our data. We have two important properties that we consider when looking at the shape of the distribution. Those two are skewness and kurtosis. I'll go into each of those two briefly. Skewness is when scores are grouped on one side of the distribution more so than the other, and then trail out from that area. I'll give an example here of a positive skew. So you'll see that scores are more frequent here on the left, and so we have a frequency on the y-axis, and then scores on the x-axis. So scores that were in the lower range were more frequent and became less frequent as the scores became more extreme. So this is skewing towards to the right, which is called a positive skew. If the scores are tailing off to the left, that's going to be a negative skew, because if we continue this x-axis, it would enter into negative numbers. So think about the skew direction as what direction is it pointing? This is pointing towards the negative numbers. We can also look at the kurtosis of a distribution. So this is the curvedness or the peakness of the graph. And so usually in a normal curve, that will be in the center point. One type of it is leptokurtic, is a Greek term, means it's very, very thin. The peak is very sharp in the middle here. We can also have a more flat distribution. So plati in Greek is flat, and so in this case, scores are relatively evenly distributed across the entire range, and so it is very much a flat distribution. Ideally, in our regression statistics, we're looking for, or generally trying to set up our studies to collect this type of data, is a approximately normal distribution. In an approximately normal distribution, the scores are most frequent in the middle point around the mean and become less frequent as you get further away from the mean. If you do a random data collection, this is generally what you're hoping to find. You'll get the skewed data sets when you're using the convenience sampling or some other type of non-random approach. So in this normal distribution, this center point, as I mentioned, is the mean. And variability, any statistic in terms of variability, will give you an idea of how far this distribution spreads from the mean. So next up, in terms of variability, it's the extent to which the scores in a distribution differ from the central tendency. So the most familiar way of reporting variability is in terms of the range. That's going to be very common in basic statistics. So for example, if you had scores 2, 3, 4, 6, 7, 10, you would say that the range of scores was a 10 to a 2 or 2 to a 10 in an effort to describe how different all the scores were in your data set. You'll often hear this when people are describing their data and they want to make the point that not all the scores were the same. Of course, there's other ways of measuring variability. First off is the sum of squares, which we'll use extensively in regression. So in the sum of squares, what you're doing here is you're taking a score and you're subtracting the mean. Basically, for each score, you're going to see how much it differs from the mean. And you could add all that up. However, that would be evened out and equal to 0, as I mentioned before. If you sum up all the deviations from the mean, it'll equal 0, because some scores will be above the mean, some scores will be below the mean, and they cancel each other out. In order to calculate the sum of squares, you look at the deviation for a score from the mean and then square it. This puts it out of negative numbers, and as a result, they won't cancel each other out and equal to 0. So the sum of squares is an estimate of variability. It'll tell you how much the scores actually differed from the mean, which is very different from the range. So we use the sum of squares in our calculations several times in regression. It is a key piece of our regression analyses and correlation analyses. Here's an example of how we can calculate the sum of squares and estimate variability. So we have our data points 57, 69, 72, 81, and 86 on the left. Now there's two different ways that we can calculate the sum of squares. I'll go back to the prior equation. We'll first do this top equation, but you'll also see the data is reported there, so you could calculate the sum of squares using this more extensive equation there. So we have the 5 variables. If we look at the average, that will be 365 divided by 5. That should be 73. And so 57 deviates from 73 at negative 16. If we look at 57 different from the 73, that'll be negative 16, but we square that to get 256. And so for each of the variables we do that. We have 256, then 16, 1, 64, 169, and we add that all up to 506. The other option is to use that other data reported, the 27,151. That is each data point x squared and then summed up. Notice that it's 27,000 right here, the sum of all of these numbers. I'll go back to the next slide. And then we have 133,000 and change divided by 5, n is the number of variables. We could sum x up and then square it and get that 133,000. That will equal 506 as well. Ultimately, we're trying to get a number that represents, of our entire data set, how much did scores differ from the mean, and this number will give us a score of 506 for those 5 scores. Variance is a key term that we'll be using a lot in terms of understanding variability. It's the index that reflects that degree of variability. It does not have the limitations of the range that we brought up before, and it is really an approximate description of it. It is the average deviation from the mean. And I say approximate, you're going to be dividing by n minus 1 because you're going to be collecting data from a sample. You do not have the entire population in your data set, so you are making some inferences, and as a result, we lose a little bit of power there in our theory of statistics, and so we divide it by n minus 1 rather than n. The disadvantage of a variance is it's expressed in units different from those of the raw summarized data, and so you saw that we just had A sum of squares of 506. What exactly does that mean? And also in terms of the variance, it's going to be in units that is different from the other summaries of data, whereas the range was a 2 to an 8. It was very easy to get your head around. So the standard deviation is the variance squared. I have the equation here for standard deviation listed below. It's a measure of variability. Obviously, it's the is the variance. I'm sorry, it is the square root of the variance. So the standard deviation squared equals the variance. It gives a valuable information to us in terms of the distribution of scores. To calculate it, you take the square root of the variance listed here is our part of our equation. We're going to be doing the standard deviation quite a bit and using the standard deviation quite a bit in correlation analysis. It's also it's very clearly represented in our normal curve, in our normal curve theory. So the standard deviation is something to get familiar with. It is, in terms of the normal curve is a theoretical distribution. So it's how we expect our data should be represented in terms of distribution. The most frequent occurring scores should be clustered around the middle, and the scores that happen less frequently should be more distant from the mean. It has very unique characteristics, and from these we can begin to draw conclusions about the people that are represented in our measurement. And so we use this normal curve as kind of our pillar of statistics, of our theory and our hypothesis testing. And so in terms of the normal curve, I have listed here a graph where you'll see the middle point. This will be the mean. Often it will be the median, or hopefully in a true normal curve, it's also the mode. So at the middle point where your mean is, underneath this bell curve is all of the potential scores. So this bell curve right here will indicate the frequency. So as you go up, that's the frequency. So the most frequent response is the mean. Down here is, as you get further away from the middle point, is represented by standard deviation. So this is one standard deviation to the left, two standard deviations to the left, then three standard deviations to the left. And it's symmetric. So it's going to be matched on the right-hand side, one standard deviation to the right, and so forth. In a normal curve, what's great about this and why we're able to make inferences and use hypothesis testing is that one standard deviation right here, we're going to consistently be able to estimate that that should be 68% or 68.26 precisely percent of our sample. So 68% of our sample will be within one standard deviation of either direction of the mean. If we expand out a little further and include it to two standard deviations, we're now going to be 95% of our data should fall within two standard deviations of the mean. Because we're using these standardized scores of a standard deviation, we're able now to calculate how far away people are from the mean and determine what your percentile might be. Also listed here is within three standard deviations is 99. So, or almost 100% is within three standard deviations. So if you're scoring two standard deviations above the mean, all the way over here, you're going to be in a very high percentile. The way that you'd calculate that is, you know that the mean is at the 50th percentile. We'd add another 34.1 and then another 13.6%. That would equal 97.7%. So you'd be almost at the 98th percentile if you were two standard deviations above the mean on some type of test or scoring. So that was an overview of some prior statistics that you likely had in terms of descriptive statistics and statistics that will describe our distribution. Thank you for listening to this lecture.